Jeff and Tomas collected the following data for a bouncing basketball. What is the rebound ratio as a percent? That's the first thing we needed to look at here. So if I look at it, rebound ratio is essentially the percent of the height that a ball recovers after it's been dropped from a certain height. Now I don't know what height this ball was originally dropped from, but after one bounce, it's at 80 feet. And then after the second bounce, it's at 64. So the rebound ratio for that jump should be 64 divided by 80. And when I do that, actually, because 8 squared is 64, I recognize that this has to be 0.8. So if I multiply 80 times 0.8, it's going to give me 64. So 80% of the original or the last height is recovered, right? And it decreases by 20%. So if I take this to the next bounce, right, I'm going to look at 48 divided by 64. 48 divided by 64, and I'm not sure what that is. 48 divided by 64. That's interesting. That's actually 75%. So it's not quite what it was before. And if I go another bounce, let's look at that one. 38.4 divided by 48. So let me see here. 38 point, not negative. And definitely not negative twice. 38.4 divided by 48. That gives me, oh, that's back to 0.8. Well, that's interesting. Two of these have rebound ratios of exactly 0.8 and one's at 0.75. And to be honest, that's to be expected. If you recall, when we were collecting data like this in class, it's kind of difficult to see exactly where the ball comes back up to. There are three values here, and I guess I don't know if this makes sense, but one of the things I could do is I could add all three of those. So for example, I could add 0.8 plus 0.75 plus 0.8, and I could take the average of those, divide by 3. What does that give me? 0.8 plus 0.75 plus another 0.8. That's 2.35, and if I divide that by 3, that's interesting. 0.8 plus 0.75. So that's giving me 78.33%, which I guess makes sense because the 75 is kind of pulling it down from the 80%. So the average rebound height for those three bounces is 78. It's 78 1/3. I'm just going to write 78.3%. And actually, you know what? I think I'm going to go with that. So I think that makes sense. So the average rebound height there is 78.3. Now, it's not going to give me these numbers exactly as I bounce, but it's a pretty good approximation. Next, it says write a model for their data and then sketch a graph of the situation. So if I was going to write a model for this situation, the one thing I need to know is the 0th term, right? As it is, I just know what the first term is. It's 80. And according to this rebound ratio, I'm multiplying by 0.783 each time I go forward, multiplied by 0.8783. So if I want to go backwards one jump to figure out the 0th term, I could divide by 0.783 and see what I get. So let's take that. Let's take the 80 and let's go ahead and divide that by 0.783. And when I do that division, I'm at 102.2. So 102.2. So if I go with that as my my 0th term, right, the initial height before the ball's bounced at all, I can write a model for it, right? And I'll just say y, the height of the ball after x bounces, is equal to 102.2, that's my initial height, times the rebound ratio of 0.783. That's the average of the three different rebound ratios I had there. and then I'm going to raise that to the x power. So again, the deal is I'm using exponentiation because it allows me to show repeated multiplication. I'm starting with 102.2 and I continue to multiply by 0.783 each time as I move from, you know, the first bounce, the second bounce, the third bounce, the fourth bounce, etc. Now, if I take a look at this as a graph, let's see, the 0th term, when the ball hasn't bounced at all, is at 102. So I can put a nice large dot there. After one bounce, I'm coming all the way back up to 80. After the second bounce, I'm coming all the way up to 64. So here's 65 is in between there, so just slightly below that, 64. And then after my third bounce, it's coming back up to 48, which is below the 50, somewhere in here. And then after the fourth bounce, it's going down to 38.4. So third bounce, 38.4, somewhere in this neighborhood. So I don't think that it makes sense to connect those dots because I don't know that it's a continuous function. Obviously, the ball is moving up and down, but I don't know what a 1.2 bounce is, right? It's bounced, and then it's bounced, and then it's bounced. So it's the maximum height after a bounce. So after it bounces one time, it comes up to a maximum of 80. After it bounces two times, it comes back to a maximum height of 64. So I think I'm going to leave that graph as a discontinuous graph. I don't think this is a continuous situation. So that's my answer for number 59 rather. So assume that a DVD player loses 60% of its value every year it is in a video store. Suppose the initial value of the DVD player was $80. What multiplier would you use to calculate the DVD player's new value? Well, if I'm losing 60% each year, that means I'm retaining 40% of the value. So again, if I'm trying to find the multiplier here for a situation where something's decreasing in value, what I do is I start with the number 1 and I subtract from that the percent that it is losing each year. So it's losing 60%. That means that it is retaining 40% of its value. So the multiplier I would use would be 0.40, right? Each year I retain 40% of my value. So that's my answer for A. For B, the question is, what is the value of the DVD player after 1 year? Okay, well that's pretty straightforward. So after 1 year, that means I'm starting with my $80 in value, and I'm multiplying that by my multiplier just once. And when I do that, I get 32. So it would be worth $32 after 1 year. That's a huge loss in value, right? But that's right, 80 times 0.40. So I've lost 60% of the value, and I've retained 40%. Now it then says, well, what's the value after 4 years? So for 4 years, I don't know why, but I feel like writing the word F-O-U-R, years. After 4 years, again, we start with our $80 and we multiply. That's after 1 year. That's after 2 years. That's after 3 years. That's after 4 years. And thank heavens we've got this lovely notation, right, that shows repeated multiplication. I can show repeated multiplication using exponentiation. So this shows that I'm multiplying 0.40 4 times. There's 4 factors of that in that product. So let me grab my calculator this time and look at that. So I'm going to start with the $80, and I'm going to multiply that by 0.4 raised to the 4th power. And when I do that, I get, that's not much money. That is, I'm going to round that to the nearest whole penny. So it's 2.048, which is $2.05, right? $2.05. So after 4 years, the DVD player should be worth $2.05. Okay. Write a continuous function v of t to model the value of the DVD player after t years. Oh, that's straightforward, right? At this point, just based on our answer for A and B, we should be able to do that, right? So C, the value in terms of t years is equal to this initial value of 8, and every single year that goes by, we're retaining 40% We're doing that for t years. So that's it right there, right? $80 times 0.40 raised to the t power. When does the DVD player have no value? Well, that's kind of a tricky question. I mean, in terms of this function v of t would never equal 0, right? It's going to get smaller and smaller and smaller. But practically, come on, you're taking a fraction of a penny, a fraction of a penny. So in terms of the function, I guess never, right? It would never reach a value of 0. However, I have it on good authority. My father-in-law has actually been disassembling things like this, and he has actually unwounding the copper wire and unsoldering things, and looking at the motors and the parts and stuff in it. There's always some value there, and you could take those parts into a recycler and get some cash for it. But in terms of this function, it would never have a value of 0. But boy, it gets small. I should put that down. Boy, it does get small. In fact, if I just went out for 10 years, take a look at this. $80 times 0.4 raised to the 10th power. Look at that. Look at that. There you go. Look at that. That's a penny, right? If I round that up to the nearest whole penny, it's 1 cent. That's 0.01 cents, right? That's not much money. Pretty close to 0. But does it ever reach there? Finally, it says sketch a graph of this function. Be sure to scale and label the axes. So first thing I'm going to do is I'm going to label this axis value. So I'll write the word value here, V-A-L-U-E. And we'll start with a value of 0. And I think $10 is a good scale. 10, 20, 30, 40, 50, 60, 70, 80. I don't need it, but there's 90 and there's $100, right? And then I'll do years down here. So this is after 1 year, 2 years, 3 years, 4 years, 5, 6, 7, 8, 9. I know I'm down at pennies down there. That's ridiculous. So let's see. And they're saying it's a continuous function. So I could go 1.3 years and get a value as well. So I'm gonna connect these dots. Let's see, at year 0, where we start out, it had a value of $80, nice big dot at 80. And then at year 1, we calculated its value, went all the way down to 32, right? Here's 35, slightly below that, so about $32. I didn't calculate what it would be after year 2, so let me do this. $80 times 0.4 to the second power. So we're down to $12.80. So there's $10, $11, $12.80. Oh, this is going to get small. Times 0.4 is $5.12. Well, okay. Then times 0.4. Oh yeah, that was the $2.05. We got that one earlier. And then, I have to definitely, we talked about, asymptotes, and clearly the x-axis here is acting as one, right? This function is very quickly getting extremely close to the x-axis, right? But theoretically, well, I mean, just in reality, it will never touch it because we're thinking mathematically, right? These lines are so incredibly thin that they have no thickness, right? But in all practicality, it's gonna be pretty close to 0 in not much time. So that is the decrease in value of this beautiful DVD player. I always just say, let's watch the things on Netflix, all right? Okay, a couple nights ago, we had a homework problem that was similar where they really tried to do a good job of explaining these different roots. And right here it says evaluate each expression below. So what I'm looking for here, for example, let's do C first, right? I'm looking for a value that I multiply 3 factors of, right, and get 27. So there has to be 3 of them. It turns out 27 is 3 times 3, which is 9, times another 3, which is 27. So this is a very nice root, right? The cube root, and the cubed root of 27 actually equals 3. Okay, and why is that? Well, because if I take 3 and I raise it to the 3rd power, I do get the number 27. This is going to take a little while before we feel comfortable with this. What about B? So something that I multiply 5 factors of, 5 identical factors in order to get to 32. Well, I'm playing with binary numbers all the time. I know my powers of 2, and it turns out that 2 times 2 is 4, times 2 is 8, times 2 is 16, times another 2 is 32. So you can see there's exactly 5 of those. 1, 2, 3, 4, 5. So the fifth root of 32 is equal to the number 2. And that's because 2 raised to the 5th power is the number 32. There's my answer for B and A. Now, A, oh, that's B and C, not B and A. A is, I'm going to multiply the same thing. I'm going to have 3 factors that have a product, 3 identical factors that have a product of negative 64. And I believe that's actually negative 4. Because if I multiply negative 4 times itself, I get 16. And then if I take the number 16 and I multiply that by the opposite of 4, yeah, that does give me negative 64. So this is the cubed root of negative 64 is equal to negative 4. And again, why? Because negative 4 in parentheses raised to the 3rd power does indeed equal 64. And then the last one here, how many, well, let's see, 10 times 10 is 100, times 10 is 1,000, 10, 100, 1,000, times another 10 is 10. Oh, that's great, right? So it is 10 times 10 times 10 times 10. There's exactly 4 factors of 10 there, and I do get a 10, 100, 1,000, 10,000. So the 4th root of 1,000 is equal to 10 because 10 raised to the 4th power is equal to 1,000. Now, I don't know if it's wise that I look at this right now, but I'm going to show you alternate notation, and this could be bad to do this so soon. But take a look at this. I've got here the cubed root of 32. I'm sorry, yeah, no, the 5th root. The 5th root of 32. That is actually equivalent to, it's the same thing as 32 raised to the 1/5, a fractional power. 32 raised to the 1/5. Now on my calculator, I can evaluate, I think, both of those. I think this calculator will do nth roots, but it's easier to do fractional exponents. So if I take, for example, 32 and I raise that to the power of, and I'll use parentheses here, 1 divided by 5, that's 1/5. Notice that I get the number 2, right? The 5th root of 32 is the same thing as 32 raised to the 1/5 power, which is equal to the number 2. Just something to think about. I don't know. I'm sure we're going to talk about that later, perhaps, but probably best to try and be thinking about the definition and kind of getting our minds wrapped around what's happening with these different roots. So Morgan started the year with $615 in the bank and is saving $25 per week. Meanwhile, Kendall started with $975 and is spending $15 per week. When will they both have the same amount of money in the bank? Well, I could come up with 2 different equations, right? So this equation could represent the money that Morgan has. Oops, I forgot the R. Sorry about that. M-O-R-G-A-N, M-O-R-G-A-N, and if I'll let y equal the amount of money that Morgan has. And we're starting with $615, and every single week we're adding 25. So look, if I want to show repeated addition, add 25, add 25, add 25. I use multiplication, right? Take a look at it, right? 25 times 0, I've added no 25, so that's 0, right? 25 times 1, I've added 125. 25 times 2, I've added 2 25s, which is the number 50. 25 times 3. I've added 3 25s, which is 75. So this multiplication allows us to show repeated addition, just kind of like exponentiation allows us to show repeated multiplication. So that's a nice linear function that shows how much money Morgan has in the bank. The other one that we have, the other person is Kendall. And we are told that Kendall is starting the year with $975, and each week she's spending $15. So you can see each week I'm going to decrease by $15 how much she has. Well, if you look at it, it's a nice looking system of equations, and in fact, probably it's a good candidate for using the equal values method. Certainly it's true that y is equal to itself, so I'm going to take this value of y, I'm going to put it over here, right? So I get, hey, 615 plus 25. That's one way to write y, right? Plus 25x. And then the other way that we have to write y, looking at this, is this expression here, right? And I can write that that's 975 minus 15x. So you can see there we go. We've got 615 plus 25x equals 975 minus 15x. So we're going to solve this for x. And I guess I'm going to begin by adding 15x to both sides. Lots of ways you could do this, but I'm going to do that. So that gives me 615 plus 30, that's 40x, is equal to $975. Now I'm going to take the 40x and I'm going to take away 615 from both sides, right? Take 615 away from the left-hand side and minus 615 from the right-hand side. That's going to give me 40x is equal to, oh, the shame, 975 minus 615 looks like $360. And if I divide both sides by 40, right, it looks like x is going to equal, divide by 40, 9. What is it? 9 weeks. So in 9 weeks, they should have the same amount of money. By the way, that means that if I take the number 9 and I plug it into these equations up here, right, I should get the same thing. So if 9 goes into both of these equations, this equation, and 9 goes into this equation, oh, I can actually say how much money they had. So let's do this. 615 plus 25 times 9, and that gives me $840. And the other one, 975 minus 15 times 9. And that also equals $840. That's super because in 9 weeks they'll have $840. They'll both have the same amount of money. Joanne claims that 2, 4 is the midpoint of the segment that connects negative 3, 5, and 7, 3. So let me quickly plot those. Negative 3 and then up 1, 2, 3, 4, 5. So there's the point. Negative 3 for x and y is 5. And then the other one is 7, 3. So 1, 2, 3, 4, 5, 6, 7 for x, and 1, 2, 3 for y. So that's 7, 3. So she claims that that point is the middle, and she's saying, where is it? It's 2, 1, 2, 3, 4. That point she claims is the middle. Well, it kind of looks like it, right? It certainly looks like it. So, you know, the one thing that I kind of like to think about is, look at, if I go from 3 to 5, right, that is a change of, oh, wait a minute. The y values go from a 3 to a 5, so that's a change in 2. So if I just cut that change in half, I could just go up by 1, right? 3 plus 1 is 4, so y should be at 4. That's true, right? 3, yeah, 3, yeah. From 3 to 5 is a change of 2. Half of that is 1, so if I start at 3 and go up 1, I do hit 4. If I go from negative 3 to 7, that's a change of 10 units. Half of that is 5. So if I start here at negative 3, I can go 1, 2, 3, 4, 5, and that puts me right there. Well, that certainly works. That's one way to think about it. Another, oh shoot, I did not want to erase my axes. Another way to think about it is I could look at the I think the book talked about looking at the slope triangle. So if I look at this, here's the run is going down, and then I've got this. No, the rise was down 2 units, and then the run is 10. So if I look at that, I go down 2 units and then over 10. So I could choose to just go half of this, go down 1 unit, and then go over 5 units. 1, 2, 3, 4, 5. That works too. So I'm keep getting the 4, 2 seems to be the midpoint. Another thing I can do is the midpoint is kind of the average of the x's and the average of the y's. If I look at my x values, right, x is -3 for one point and it's 7 for the other. If I add those two numbers up and divide by 2, look what I get. -3 and 7 is 4, and 4 divided by 2 is actually 2, which is interesting. Wait a minute. Yeah, that's interesting because I wrote the wrong point down right here. This is the point 2 comma 4. Thank you. It's interesting because I was wrong right there. But notice that that is the average of the x's, right? And same thing for the y's. If I take my y values, I've got one y is 5 and the other y is 3. I add those up and divide by 2. I get 8 over 2. 8 over 2 is equal to 4. So you can see that the y value is 4. And sure enough, the y value is 4 right there. So lots of ways to think about it. Please do think about it. Don't just think, oh, what's the rule? Just use your brain to kind of noodle your way through it. You can figure this out. All right, so let's take a look at this. It says identify each pair of triangles below is if it's congruent or not. Remember, the diagrams may not be drawn to scale. Please justify your conclusion. So the first one that we'll look at, and I'll try and make these a little larger here, is A. And certainly I've got two pairs of congruent sides, and because they share this side, right, that has to be congruent as well. So if you look at it, what we have there is definitely side, 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 which is one of our 5 congruence conditions that we've discussed in the class. So these are definitely congruent by side, side, side. One of the sides there is congruent to itself by the reflexive property. But other than that, we're good to go. Now, on this one, it's a little problematic for me. One of the things I know is that these angles here and here are congruent because they are vertical angles, right? Those angles that are right across from each other. So I do have an angle, and I've also got 2 pairs of congruent sides. But here's my problem, right? I don't have side angle side, right? I mean, if this was 4, I'd be set, right? I could say they were congruent by side, angle, and then side, right? I'd have the 5, the angle, and the 4, the 5, the angle, and the 4. But I don't have that. So there's just not enough information here. Like, even if they told me some of these opposite sides were parallel, I could go further. But right now, I just have to say not enough info. Yeah, I say info and then I write the word information. I don't know what's up with that. Let's see this one right here. Oh, interesting. This is tricky. I like this. I didn't see this coming. So they've shown me that these little pieces off on the side are 3. And I'm going to mark those up too. I'll mark those in green. So this little piece right here is 3. And this little piece right here is 3. Right? So look at the piece that's orange, right? Both triangles have that in them, right? And I don't know what that is, but it's some value, right? And if I take some value, let's just say it's x, right? Let's say it's x. Well, if I take x and I add the green, right, I've got an x plus 3 in the top triangle. And if I look at the bottom triangle, there's the green plus that thing that's orange. I've got an 3 plus x there. Well, these are the same. So you can see I've got sides in those triangles that are absolutely the same, right? And in fact, if I like to kind of sketch these separately sometimes. So if I pull off that top triangle, right, because these are the same, right, there's like the x plus 3 and the x plus 3, and I've got this angle, and I've got that angle. And then I do the same thing down with the bottom one, right? I'll pull this one off. Oops, didn't like how I drew that. It's too long. I'll draw this and like that. So if I look at this, I've got this angle, I got this angle, and then I've got that side that connects them. So these are definitely congruent by the angle side angle method. It's a little tricky though because I've got to make this argument about these x plus 3 and 3 plus x being the same and giving me those congruent sides. But definitely that argument can be made. Last question here, we've got a beautiful, oh, look at that. It's a 90-degree angle. And you can see definitely they said this is not drawn to scale, and for sure it isn't because that does not look like a right angle. If that's a right angle, I need to talk to the contractor who built my house because I got problems. But anyways, if that is a 90-degree angle in the diagram, right, I clearly have congruent hypotenuses, right? If that's a 90-degree angle, these are right triangles. And they share this leg, right? So these would have to be congruent by hypotenuse leg. That's beautiful. So we've got side, 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 not enough information, angle, side angle, and hypotenuse leg. And last question for the evening. Tickets for a concert have been incredibly high demand. And as the date for the concert draws closer, the price of the tickets increases exponentially. All right. The cost of a pair of tickets was $150 yesterday, and today it's $162. Okay. You know what? From that information alone, I'm thinking we could figure out the multiplier, right? So what does it say? It says the cost of the pair of tickets was $150 yesterday. And today, it's at $162. So it's definitely a percent increase, but what percent increase? You know, if I take 162 and divide it by 150, well, that is, yeah, let's see, 162. Let's turn on the calculator. 162 divided by 150. That gives me 1.08. Okay, so my multiplier is 1.08. That means they're increasing by 8% each day. Right, I can see my multiplier, and it is a percent increase. Okay, so let's see here. As you complete the parts below, assume that each day's percent increase from the day before is the same. Okay, so I don't have an increasing percent increase. The percent increase is going to be the same. And I know that already, right? What is the daily percent increase? What is the multiplier? Okay, so A, the daily percent increase is 8% daily increase. And the multiplier is 1.08 multiplier. Yeah, multiplying by 1.8 each time. What will the cost of a pair of concert tickets? A pair of concert tickets 1 week from now. What will be the cost of a pair? What? Have we been talking about pairs the whole time? Oh yeah, it is the cost of a pair. So we're talking about pairs of tickets, right? No one wants to go to a concert alone. Let's see. What was the cost of a pair of tickets? No. What will be the cost of a pair of tickets 1 week from now? Okay, well, this is today. This is my today, right? When it's 162. So I'm going to say, geez. The concert today. So that multiplier I have is for days, right? So I'm gonna write a function here for this. I'm gonna write something here. Y equals 162. That's where I'm starting at today. This day is today times my multiplier 1.08 raised to the x power. Now I got to be careful. X is in days. It's not weeks, it's in days. So it says, what will be the cost of a pair of tickets 1 week from now? That means in 7 days. So that should equal 162 times 1.08 raised to the 7th power. Okay, so let's try that. $162 times 1.08 raised to the 7th power. And I get $277.64. Okay, so that's equal to $277.64. All right. Today I could have got them for 162. Okay, so what was the cost of a pair of tickets 2 weeks ago? Oh my gosh. 2 weeks ago. So that's in the past. In the past. Oh, I know. I actually know because x can be a negative number, right? We've already talked about these negative exponents. So if it's 2 weeks ago, 2 weeks in the past, that's negative 14 for x. So let's do this. So c, y would equal 162 times 1.08 raised to the x power, but this time my x is going to be the negative number 2 weeks, right, which is 14 days. So negative 14 days. How cheap could these tickets have been? Let's see here. 162 times 1.08 raised to the negative 14th power. Oh, $55.15 if I was rounding to the nearest penny. So I get $55.15. And I know, let me just double check here. I got 162 times 1.08 raised to the negative 14th power. So that should be 2 weeks ago. All right. So, and I totally do not like how my 5 looks. That's terrible. Let me write that again. $55.15. There we go. So that would be the cost 2 weeks ago. And to be honest, I don't know the concert, but that seems like that could, let's see, D says, what will the cost of a pair of tickets be 2 weeks from now? Didn't I already answer that? Oh no, I answered 1 week from now. What will be the cost of a pair of tickets 2 weeks from now? Does your answer make sense? Why or why not? Okay, so 2 weeks ago it could have been $55. That would have been great if I would have bought them. Maybe that's when they went on sale. So let's do D and we'll finish this. On this one, this time it is 162, but it says 2 weeks from now. So instead of 7 days like I did before, I'm going to do 14 days into the future. So what would these tickets cost? I just lost my calculator. There it is. So let's bring this up here, and now I'm going to take the 162 times 1.08 raised to the 14th power. $475.83. $475.83. I have no idea if that's reasonable. I can't imagine, well, I'm just thinking myself, right? I can't imagine I would ever spend that kind of money on a pair of tickets, but I imagine there probably are people that do that and they wouldn't even think much of it. But what does it say? It says, does your answer make sense? Why or why not? Well, to me, it doesn't make any sense at all. Are you crazy? $475 for a concert? Just buy the DVD, or you know, buy just buy the MP3 file or whatever. Buy it on the what's that called? The Apple. Buy it on the iTunes store. You can tune that in on the iTunes, and I guess it's not the same as being there. But anyways, I'll quit rambling on. That's my take on that question.